Good evening, everybody. And so, just before I begin the talk, it's just a disclaimer. This is not sponsored by any of the political parties, and I'm not here to influence you to vote for any of them. But at the end of the talk, you may realize how you have been already influenced. And with that ominous introduction, and this is my thesis title: Influence Dynamics on Social Networks. This is work done under the guidance of Professor Anurag, Kumar. And so let's get started with the talk. So basically, I'll give you an introduction to the framework of influence dynamics, and then I'll go through 4 different problems that I've attacked, and the necessary introductions will come along the way. So I think none of you here need an introduction to social networks, but networks in general have been a pervasive theme in the past decade. So from the data that has been gathered across natural and man-made systems, people have started modeling them as networks. So for instance, in the natural systems case, you have protein interaction networks and food webs in the ecological system, or even the neuronal networks. And in the man-made case, you have the air, road, or rail transportation networks, you have power grids, and the internet, of course. And one of the networks that's most intuitive to us is social networks. Basically, a social network is a graph where individuals are the nodes, and the relationship between the individuals are captured by the edges. These edges can be directed and or weighted. So direction, for instance, in the employer-employee relationship, the edges are directed, and the weights could indicate the strength of a relationship. And some other non-intuitive social networks are, for instance, your email contact networks, or in the context of research community, the co-authorship networks. So there's an edge between two authors if they have co-authored a paper, and the more co-authorship and the stronger the edge. So there has been a lot of interest in this area for the past decade or so because of massive active user base in online social networks like Facebook and Twitter. So social network analysis is basically the area of studying structure and dynamics of social networks. So based on the data that has been gathered, there have been several structural properties that have been observed. For instance, social networks exhibit something called a small world property. Basically, the path lengths in a social network are very short compared to what you would expect in a regular graph. And social networks also exhibit a high clustering property. Basically, if you are friends with nodes A and B, then high likelihood that A and B are also friends. So basically, you will find a large number of triangles. And finally, social networks also have something called a scale-free degree distribution, which means that there are very few nodes which act like hubs and have a very high degree, whereas a large number of nodes have very few edges. And there have been several generative models for coming up with synthetic social networks, and I wouldn't go into the details of that, but these are about the structures. There is also a study of dynamics of the networks. So network dynamics is basically how the edge structure evolves and how the network densifies over time and how communities get formed. But the focus of this thesis is not on dynamics of networks, but it's actually on dynamics on networks. So you're given a graph and you want to study some processes that happen on these graphs. So for instance, the thesis would be about characterizing cascades on networks. So modeling these will give us an idea of how influence spreads on the network, or information, or epidemics, or even, understanding this could help you even get higher citations in your citation network. So influence spread models have been traditionally in the sociology literature dating back to 1978, where they have studied how people behave in a riot scenario, how influence between people actually triggers others to take part in riots. This area restarted to say so in 2003 when this was proposed in the computer science context of maximizing the influence spread. So this is a problem that we'll start working on, and this comes up in the context of viral marketing. So if you want to popularize a book or a movie or something, you want to find out the most influential nodes in the social network to whom you can target your campaign. And there are 2 widely used models for understanding how the influence spreads. So these 2 give you a caricature of how these works. So one is the threshold model, which can be thought of as a pull model. So for instance, if you look at this, this user J says that I will switch to Android smartphones if a sufficient number of my friends have already switched. So this sufficient is not just the number, but it's a weighted combination. It depends on how much influence each of your neighbors has on you. And it also depends on how susceptible you are to the influence of your neighbors. So there are two quantities that come into play. One is the weight of the edge, and the other is a property associated with the node, which is theta j. We'll explore this in detail. So theta j is like the susceptance to the influence of your neighbors. Whereas the other model, which we will not look at, but it's nice to look at just the idea of what the other model is. It's called the independent cascade model. Here it's more like a push model. So say Node J watched Game of Thrones and got really interested in the TV series, and he's going out and suggesting it to all his neighbors. So here each of these edges, the weights can be thought of as probabilities. So Pji is the probability that when J tries to influence I, he succeeds in influencing I. So in this graph, if you can see, these two nodes got influenced by J, whereas these three nodes are still susceptible. So these are the two models, but the entire thesis will be looking at the linear threshold model. So to go into the formal definition of linear threshold model, you have a graph given by V comma E. It's weighted and directed, and we have the weights adding up to 1 into any of the node. All the incoming edge weights add to 1. This is because this was proposed by Kemp in 2003, and this model basically is because each of the thresholds, the node samples, is from 0 to 1. So it's like how much influence do you get is compared to what is your threshold chosen from 0 to 1, and you get activated based on that. So to be exact, basically you start with an initial set of nodes which are called the seed nodes, from which the influence spreads, and then at any step k, a node will get activated. Activated means it gets influenced by its neighbors if it has been inactive till k minus 1, and the influence from the set of nodes which are active at k minus 1 just pushes over the threshold. So the total weight coming into the node is greater than theta j. This will not actually exhaust the entire network. There might be nodes in the network whose threshold will never be crossed. They might have their threshold very high. So the process actually stops when a terminal set is reached, beyond which the influence cannot spread. So the expected influence is basically the expected size of this terminal set. And so the problem of influence maximization is basically this. You start with a set, you are given a budget of k nodes. You start with, you want to maximize the expected influence, and you want to pick, it's a combinatorial problem. You have to pick k nodes out of the n nodes such that your expected influence is maximized. And this problem has been shown to be NP hard, and it can be reduced to vertex cover. And it can also be shown to be monotone and submodular. Monotone basically means if you take two sets A1 and A2, A2 is a superset of A1, then the influence of A2 is greater than influence of A1, which is obvious to understand. But and the second one is submodular. It's basically saying that it's a diminishing return property. Basically, you can think of it as an equivalence of concavity for set functions. You have diminishing returns as the set size increases. So for this problem, the basic network heuristics actually don't work really well. So you have to go to a different approach. Network heuristics basically mean look at the node which has the highest degree, or look at the node which is closest to most of the nodes. So those actually perform poorly, and Kemp et al. Actually proposed an algorithm called the greedy hill climbing. Basically, you pick a single node which is the most influential, and then add to it nodes which are incrementally the maximum influence. So marginal influence is maximized at every step. And they can show that this achieves a approximation guarantee of 1 minus 1 by E, but it is computationally expensive, this algorithm. So there have been several other approaches to either improve the greedy algorithm or propose much easier, improve the computation of greedy algorithm, or propose easier computable heuristics which can replace the greedy algorithm. Our approach is basically to look at the LT model in detail, look at the analytical properties, and then derive an algorithm out of it. So basically, what you want is, if you start with a set A naught, which is the initial set, what is the probability that each of the other nodes get activated? You just sum all these probabilities, you get the expected influence of that initial set A naught. So this is more intuitive to understand from the theorem that we have. Basically, if you want to find out the expected influence of node J in this node I in this network, all you have to do is partition the problem into two. So you get one for the node I itself, and then you just take a network without node I, and treat each of its neighbors as the seed. And then you look at the influence of node j in the network without I, and then look at the influence of node k in the network without I. So you just then add them in a weighted combination, because I gets wij of whatever j gets. So this is the way in which you can then actually expand it, and then you get a recursive expansion of the expected influence. So the same thing can be done if you start with the set A naught. You can actually partition it into k different problems, where k is the set size, and each of the problems is basically retain only one of the nodes and remove all the other nodes in A naught along with its edges. So find the influence of I in this graph and find the influence of k in this graph, and then add them, you get the influence of I comma k in this graph. Or alternatively, what you could do is you can actually collapse all these three nodes into a single node, and then appropriately change the edge weights. So you can then solve it as a single node influence computation. Now the point is that from the expressions that we have, it's easy to see that if you want to compute influence of I on k, that is a property that k gets influenced starting from I, then it's basically sum of product of path probabilities. So you just take all the paths from I to k which are not cyclic, so acyclic path probabilities. So you have this path which is wik, and the other path is wij into jk. So you just sum all these, you get the probability that k gets activated, and this gives a nice interpretation in terms of Markov chains. I wouldn't delve too much into it, but basically this gives you an idea of the well-known algorithm called PageRank, which is used for ranking web pages. There have been proposals to use that for influence maximization, and this gives you an idea of where PageRank will actually work. I will not go into the details of that, but so the question here is more of, so another interesting result that you get is, for instance, if you take an acyclic undirected network, so you have a graph without any cycles, and the edge weights are actually special in this case, where edge weight into any node is basically 1 over its degree. So if it has n neighbors, each of the edge weight is 1 over n. So in such a network, you can actually say that the influence of node j is just 1 for the node itself and the degree of it. You need not actually compute the exact, the influence across the entire network. You just look at the degree, and then you can say the total influence is di plus 1. So here is an interesting way in which the local property of the node actually governs its global property, which is the influence. So here we come to the influence maximization problem again. So from the expressions that we have, you know how the influence can be computed recursively. So we will be using that to actually propose an algorithm for maximizing the influence spread. So the difficulty with greedy algorithm is basically that you have to compute the influence for each stage. You have to compute for all the remaining nodes of so basically n minus k plus n minus of k minus 1 sets, or each of size k, and this has to be repeated k stages. So this each influence computation is actually very expensive. So what you can do is you can start with the first greedy set, which is basically rank the nodes by their individual influences. Just take one node at a time and then find their influence and then rank them by that. You might think that you can pick the top k nodes of that, and then you can use that as your influential set, but it turns out that there will be some dummy nodes there. Dummy nodes are like these. For instance, if these red nodes are highly influential nodes and the blue nodes are not so influential. So here, if you compute the influence of this blue node, it will be actually high because it has influence on these three highly influential nodes. Whereas if you have already picked these three nodes in your set, you don't have to pick the blue node, because blue node does not have any influence other than from these nodes. So we will call such nodes as leechers. They leech influence, but they are actually dummies. And there are also subordinates, the converse of that, where this is a very highly influential node. Once you get them, these nodes are not so important. So all you have to do is you take this G1 list, which is the rank ordered list of single node influences, and then use these insights from the analytical expression, and you actually sort them. You actually sieve through the list. Basically take an initial node and then look at all the nodes which are leechers or subordinates of that node, remove them, and then you again restart with the topmost node. You keep doing this, you can actually show that it actually performs. Okay, you can actually show that the performance actually reaches the greedy performance. So this was actually evaluated on a co-authorship network, where the edge weights are basically proportional to the number of papers that they have co-authored. And here you can see the performance of, so this red one on the top is the greedy algorithm, and you can see that G1 without sieving, which is black, which is basically just the list of nodes with their single node influences and the top k. and it actually performs quite bad because there are some dummy nodes. And this alpha is the pruning factor. As you increase alpha, you're becoming more and more strict. So when alpha is equal to 0, you're still somewhere here. No, wait. So here, the alpha is this comparison value. So if alpha is close to 0, then it means that you are actually being very strict, because you are saying that any node which has greater than this, then remove this, remove the node from the network, remove the node from the list. So you're pruning it out. So smaller alpha means you're being very strict, and so there is an optimal alpha that you have to operate at. But it's easier to actually sweep through the values of alpha, and here it turns out that alpha equal to 0.3 gives you a really good approximation of the greedy algorithm. The advantage is here that in each time step, I mean in each iteration of the greedy, you're going to compute only of k time greedy algorithm. So this is our first work where we have actually proposed from the LT model. So the next work is basically based on the threshold model itself, but the threshold model actually is there in the sociology community since the 20s. The point is that in threshold models, if you look at the Kemp model, the threshold was uniformly distributed, and the problem was of algorithmic, combinatorial problem, where you have to find the most influential k node. But the sociology community was more interested in how the innovation adoption trajectory is. So if you look at any product, you actually have this. This is something called the Rogers bell curve, where it shows how product adoption takes place over time. So for instance, it's the innovators who take it up first, and then there is the early adopters, then there is the early majority, then there is the late majority, and then the laggards. So for instance, so here is the time evolution of adoption, and you can show that you can, from data they have looked at a lot of bell curve kind of features where the early majority and the late majority are the significant portion. For instance, if you look at this slightly dated graphic, you can see that technologies like TV and newspaper are far on the right, whereas Facebook was somewhere in the middle, Gmail is on the right, and Android and Amazon Kindle are on the left, which basically says what fraction of the population they have already covered. So basically this bell curve captures the incremental change in adoption, and the S-shaped curve is the cumulative of the bell curve. So basically from this you can say that from the threshold interpretation you can say that the innovators are those who have very low thresholds, and as it goes up the thresholds are higher. Since they have very low threshold, they adopt the product very quickly even without a lot of influence from their neighbors. So there is necessity to understand this model for a general threshold distribution, which Kemp does not actually allow us to do, the Kemp framework. So we actually go to the other framework. This was actually addressed in Granovetter's work, which actually studied general threshold distributions. So what they did was, what he did was basically if f actually captures the threshold distribution, the CDF of the threshold, then you can say that at any point of time, if x nodes are already active, then the set of nodes whose threshold is going to be less than x is going to be f of x, because f of x is the CDF. So you can actually find out how many nodes will get influence at the end by actually solving this fixed point, which is x equal to f of x, where f is a CDF. But the problem with this kind of approach is that the thresholds are, if you actually look at the evolution of the model, the thresholds are getting resampled at every time, but people generally don't resample the threshold. The distribution is basically to model the uncertainty in the threshold. Therefore, this does not actually fit directly into the Kemp framework. So, and one more thing is, if you take the uniform distribution as your f, then this fixed point dynamics doesn't say anything. It just says x equal to x. But we know that from the Kemp framework, if you start with the uniform distribution, you can actually get a significant increase in the epidemic. So now we want to look at a general threshold distribution, but from the Kemp framework of progressive influence spread. So what we do is we actually go back to the Kemp model, but instead of a general, so this Granovetter's work looks at all see all kind of a system where there is no graph. People actually can see all the others acting, and therefore the influence is completely homogeneous and complete. Therefore you go back to the Kemp model and take a network which is complete, and all the influences are homogeneous. So each user has the same influence on all his neighbors. So you can actually study the same kind of influence maximization here, but it doesn't make sense because all the nodes are identical. So for the same reason, you can actually forget about which sets you are targeting, but all that matters is the number of, only the size matters because all the nodes are homogeneous. And so if you take this kind of a system, now what we can do is, the Chem framework also gives you an idea of only the terminal influence. If you start with this set of nodes at the initial set, what will you get at the end of the process? But an interesting thing that, I mean, a more useful thing is basically how it evolves over time. And to do that, we actually go to, I mean, this framework actually allows us to do that. And we can see that this set sizes Bk and Dk, which are basically the incremental set sizes. Dk is at the time step k, how many nodes got influenced. And Bk is the set of nodes that got influenced k minus 1. So Bk is accumulating Dk every time step. And you can show that Bk Dk is a Markov chain. Now for getting the trajectory, what we do is we actually use something called the Kurt's theorem, which gives you an approximation of the Markov chain in terms of ODEs. It captures the average trajectory. I'll just give a brief introduction to Kurt's theorem. Basically, for ECE people, this is the well-known model, where this state is based on Q, where lambda is the arrival and mu is the service process, and the state is basically the Q length. So the Q length process x of k, you can actually look at this same system. You can speed up the system n times. So what you do is, instead of looking at x of k, you look at x of nt. So basically you are speeding up the process n times, and then you are actually going to scale down the process also. So if you look at this graph, it gives you an idea of how it does. So for n equal to 10, the magenta curve captures what the behavior for n equal to 10. As n becomes larger and larger, the behavior becomes more and more final. And this is where Kurt's theorem comes in. It says that as n goes to infinity, you can actually show that this trajectory goes closer and closer to the ODE. In this case, the ODE turns out to be something like this, just lambda minus mu times an indicator function. And in this case, if lambda is less than mu, it's like this, and if lambda is greater than mu, it's like this. So it's nice to actually capture the entire dynamics of the system in terms of an ODE, so that work on the ODE, you can the optimization problems are easier to solve in the ODE domain. So what we do is we adopt the same approach for the HILT model. So we have a Markov chain in terms of Bk and D. We have to do ifs, and then Kurt's theorem to get the ODEs. But it turns out to be because the scaling that we did here was just twofold. We actually made it more refined in terms of time, and we also scaled down the amplitude. But it turns out the amplitude isn't sufficient convergence in our process. So what we have to do is we also have to use something called a probabilistic scaling. So basically, you want to slow down the process further. What you do is you take one time step of evolution in the HILT model. So this is k plus 1, and instead of allowing all the nodes dk to influence in the time step in this duration, you partition the time step into n mini slots. So what you are doing is you are in addition to scaling the process in terms of time, you are actually going to slow down the process dynamics by saying that not all decays actually influence in each of the time slots. They only 1 over n in decay actually tosses a coin, and then with 1 over n it exerts its influence. Else what we have done is in the expected sense, only dk over n is actually exerting influence at every time step, and this allows you to the process even further, and convergence of the problem, convergence of the Markov chain to the ODE. So this shows the dynamics of the scaled process. So you can actually show that. So these are the equations of interest. So basically, you can show that the evolution HILT model under a general threshold distribution F. So you recall the Granovetter model where he said the terminal value would be just the fixed point of x, but it's not so simple that it's actually a result of this ODE. So basically, you just plug in HF, which is the hazard function of threshold distribution F, which is f of small f of x by 1 minus capital F of x, the PDF over 1 minus the CCDF. So this ODE actually captures the average trajectory if the model is HILT and the threshold distribution is F. So what does this ODE say for the, so here is here are some plots where you can see that as n increases, n is basically the resolution to which you are scaling the process. So as n increases, and it's also the system size. If you look at model, the number of nodes in the network is basically, and the system is scaled with the same factor n. And as n increases, you can show that the trajectory is closer and closer to the ODE trajectory. And so basically, if you have a social network which has, so for instance, if you look at networks like Facebook and Twitter, they have millions of nodes. Facebook has more than billion nodes. So here it turns out that for n in the order of thousands itself, you actually have a really good convergence to the ODE. So once you can capture such behavior, look at a homogeneous, address all the optimization problems in the ODE domain itself. And so for instance, and then you can look at various, so since we have got an expression for a general threshold distribution, you can actually look at the effect of the threshold distribution by plugging in different threshold distribution. For instance, the Kemp model actually uses the uniform threshold. So when you actually plug in the uniform threshold distribution, the HF is by 1 minus x, and you can actually explicitly solve the trajectory of influence. So since you have an explicit solution of B of t and D of t, you can actually address questions of time constrained optimization. So for instance, in the Kemp model, we were asking questions of maximizing the terminal, but time step after say 2 days, I want to know maximize the influence. So what kind of initial parameters should I start with? Those can be addressed because you have a average trajectory captured here. And another interesting thing here is that if you start with the exponential distribution for the threshold, then you actually get this ODE, and I think people from either ecology or actually see that this is the SAR model where S is infected and recovered, and models in epidemiology. And it turns out that you start with the LT model, which is on a graph, and under the exponential distribution, it actually to the epidemic model of S. The first models to the epidemic model. And here is some comparison. I mean, here is a plot which shows how the parameters of the system actually interact. So two threshold distributions, one is exponential and the other is uniform, but both of them have the same mean. So say the population is distributed 0 to 1 uniform, then so this red curve captures how the influence spreads in the population. What if the population has lambda equal to 0.5? So exponential has a lot more mass near 0. Therefore, you would expect exponential to have a significant lot more users who have a very low threshold. But it actually turns out that, I mean, this is in the case of, so there is another parameter. One is the F, the distribution. The other one is how tightly the network is coupled. Gamma captures how tightly the network is coupled. So gamma actually increases. Gamma is basically the influence weight of any single edge. So if gamma goes closer and closer to 1, in uniform distribution you can see that all the users threshold are distributed are in the interval 0 to 1. So when you go closer and closer to almost all the users in uniform distribution, you can show that when gamma is equal to initial node to get to cover the entire population. But in exponential distribution, since the support of the thresholds is unbounded, you can show that whatever gamma you distribution. So we have also looked at a couple of other distributions which are generally used in the hazard failure rate analysis and all. So one interesting thing to notice here is basically how you can get a, so generally epidemics are diminishing returns kind of curve, but there is also another kind of epidemic that you generally see, which is critical mass. So basically the epidemic actually stays almost flat for some critical mass, it shoots up, almost covers the entire population. So this kind of thing is generally heterogeneous networks where spreads in then, but in the first in which homogeneous system, because there is a diversity in terms of the threshold distribution, you so for instance, if you look at the available distribution, look at the blue curve where the threshold is distributed like this. So there is a significant number of people who have their threshold distributed here. So if your network is not so coupled, if gamma is kind of small, then you don't actually start influencing these people at all. You actually stay only here, and therefore the epidemic actually doesn't spread at all. You start with 0.2 and you end with only 0.2. Whereas if you have a significantly larger gamma, which is here it's 2.5, so what happens is you start spreading till this, and it's actually flattening out because you're still operating in this regime. But once the critical mass of users have been accumulated, you actually hit this major chunk of users whose thresholds are distributed here. So you get another peak here, and you can see that the D function, which is the incremental change, is non-monotonic here. It actually has 2 modes. And this is for the log logistic distribution. The only difference here is that, I mean, the way this actually comes in is because of the hazard function. Hazard function basically says how likely to get influence till this point. And if the threshold distribution exhibits that nodes are more at a point of time. Whereas, so basically, increasing hazard this kind of a property. And log logistic, you have a non-monotonic hazard rate function. Therefore, you have a slightly lesser peak here for the same kind of parameters. So we've also studied the same system in multi-class settings, but I wouldn't go into the details of it. Basically, instead of homogeneous class system where the relative community epidemic in the entire system. And with this, so basically we have studied the influence spread model in 2 contexts. Basically, one is maximizing the influence spread, which is a combinatorial problem. Second one is finding the, characterizing the trajectory of influence. Now, the ECE people might be asking, okay, this is interesting to capture epidemic spread and influence and viral marketing. How is it useful for someone who is working on mobile networks or something? So here we are actually capturing an example where there is a need for understanding influence evolution in a mobile peer-to-peer kind of setting. So, so for instance, all of us have smartphones with us, so and most watch media content on it. So the direct delivery of media content to the smartphones is, and an alternative is basically peer-to-peer delivery. Basically, if I want to watch a video and then the same video someone else also wants to watch, then I can download and then I can transfer it to the other person via peer-to-peer link, via Bluetooth Wi-Fi. So one more thing is a single item of content might be of interest to several users in the same area. For instance, if I want to spread the slides of the talk, so I can 5 people and then among the rest spread it among themselves via their mobiles. So basically you have a multi-hop and opportunistic network because the links are not actually always there. They get formed when the nodes actually come in contact with each other. So this is a context of coupon delivery where basically imagine you have an app in your mobile where you can actually maintain a wish list of the products for which you want the coupon. And you can actually share these wish lists with peers when you meet them on your mobile, when both your mobiles come in contact. And you can also receive coupons for these products. So basically you have something like a wish list maintenance service and you have a peer recommendation because you can share wish list, and whenever someone has the coupon that you want, you can receive it. So for instance, if you look at this context, if you have node A which has, there's one book that node A, node B are interested in, but node A wants the book and it's actually recommending it to all. So whenever its mobile meets another mobile, it actually sends the recommendation, and it also has with it. So node B is actually not aware of the book. So when these 2 nodes meet, their wish lists are exchanged in a peer-to-peer fashion, and node B comes to know that A is recommending the book, and with some probability node B actually switches its state to want. So basically it says that I also want the book. I also want the discount coupon for the book. So once this is done, it updates the wish list to node A. Now if node B actually wants the coupon, node A already has it, therefore it can give it to the node B. Else, here is the interesting part, that node B does not want the book, but I can say that node A can give it to node B. Node A can say you don't want the book's coupon, but it would be helpful for the system if you can actually carry the coupon with you, because the coupon is more available in the system. So basically I'm asking node A to use node B as a relay in the network. So there is a probability with which node A will copy to node B even if node B doesn't want it. So here the question is basically like this. So you have a population of nodes which are meeting in a Poisson point. So pairwise meetings are independent Poisson processes. So the coupon needs to reach a set of destination nodes. But these destination nodes is not a fixed set, but it's actually increasing because people are actually exchanging their wish lists, and therefore the interest in the content is actually increasing. And you can actually use the nodes that do not want the content as relays. So the objective here is basically you want to quickly spread the content to the nodes that actually want it, the destination nodes, and you can actually exploit the relays for forwarding it, but you don't want to over exploit the relays because the relays might require an incentive for actually functioning as relays. So this is the optimization problem, and so basically here you have any node can be in one of these 6 states. Basically it either has the coupon or does not have the coupon. And in terms of whether it is interested, it may be interested but it's not recommending to its neighbors, or it's interested and it's recommending to neighbors, or it does not want the coupon, it's not interested at all. So this is again a continuous time Markov chain, and you can except that it is also control, because the sigma is the control that you are going to use, and you can actually use the same kind of Kurt's theorem analysis in this setup. So you again get a set of bunch of ODEs like this. So it's easier to understand what happens in these graphs. Basically, these multiple red curves actually show how again the convergence of the scaled system to the ODE trajectory. The red curve is basically the demand, the destinations that you want to reach. The blue curve captures the supply, how many nodes you have actually given, and green curve is basically the exploitation, the number of relay nodes that you have exploited. So for instance, if equal to 1, that is you are very active, I mean you are flooding the network basically, irrespective of whether a relay wants it or not, you give it to all the relays. So in that case, it turns out that the blue actually hits the red very, means you are meeting the demand very quickly. The exploitation is also significantly high, so you are using a lot of relays. Whereas if you actually reduce sigma, you can actually see that the exploitation is not much, but the target reach very late. So there should be a sweet spot between these two, and you can actually go to a richer space of sigma. Here we are actually looking at a single probability which says sigma is constant across over the entire process, whereas you can look at sigma of t, which is basically time varying. You can say that till this time you actually use this sigma 1, and then after some time you use sigma 2 and so on. So can you actually find an optimal policy in that space? An optimal policy is basically a trade-off between these two. How quickly the supply catches up with the demand, and how much exploitation you are using. You want to minimize the second one and minimize both the terms basically. Sigma is the probability with which, so sigma is the probability with which the content is copied to a node if it's a relay. Yeah, relay is a node that does, yeah. So in this case, now we are looking at the space of all sigma of t, which is the control copy probability, and you can actually show that. So the cost function that I was talking was this. So t sigma is the target reaching time, how quickly you reach the target, and this y sigma of t sigma is the exploitation, how much what fraction of relays actually have the content at the target time, and you want to minimize suitably weighted combination of this. And you can actually show that the best policy to do in this case is something like a time threshold policy. So you can actually use sigma equal to 1 till some time, time tau, and then use 0. Basically these are called bang policies, because they basically say that all the effort, whatever effort you are going to put in, put it at the beginning, because the effort that you are going to put at the end is not, I mean, if you copy to a relay very close to the target time, then that relay is not so useful for you in delivering the content, because you are going to reach the target in the next few seconds or so. And secondly, those relays will, so another interesting thing here is that the relays are actually getting converted also. The nodes which don't want the content will receive it as relays, but at a later point of time might be influenced to become interested in the content. So it's like you get a movie in your hard disk, and then you don't want the movie first, your friend is asking you to serve as a relay, but at a later point of time another friend influences you, and then you get interested in the movie and you already have it. So those relays don't actually count as a cost for you, because it is a destination which has already received the content. But the problem is that if you copy to a relay very late, then there is no chance for such a relay to become a destination also. So the optimal policy is basically to put in all your effort in the beginning, and then it's a time threshold policy. And to find the exact threshold, a destination. No, I look at just the cost at, sorry, just y sigma of t sigma. At the target time, how many relays still have it. So I don't accumulate it over time. Destinations don't become relays. Which one here? Okay. So the incentive is something like this. So for instance, if you're given the coupon, say you want to buy the book, and you are acting as a relay now. So if you become interested in buying the book, you will immediately place an order using the coupon. And basically, anyone who spreads a coupon actually believes that not all the coupons will be reimbursed. So he actually spreads thousands of coupons, and he expects only like 50 to 60% to be reimbursed. So what he says is that the coupon is valid only till the offer is valid till stocks last, something like that. So what happens is that is the target time. So once the person has spread so many coupons, and so many coupons have been reimbursed, all the relays which help spread the coupon can actually send it back to the server and actually ask for some reimbursement, saying that I actually participated in the system and I didn't want the book. So this is a coupon which is no longer valid. So give me either in terms of credits within the system or in some other form. So how y sigma acts. So and once you know that it is a time threshold policy, you can actually numerically sweep over the time thresholds, and basically it says that the time threshold is time till which you are going to copy to relays. So if you're going to copy to relays for a longer time, then your time to reach the target is going to drop significantly. So this blue curve is basically this t tau, which is going to, because you're becoming more and more aggressive, so you will come down very quickly, but it happens only till some time, because even if you copy till say time t equal to 100, the process is already over around time t equal to 20. So it actually monotonically decreases. Y tau, on the other hand, monotonically increases because as you become more and more aggressive, more and more nodes become exploited, and they remain as the target, the relays that have to be reimbursed. So basically the optimal point is somewhere in between, where you have to minimize this term, which is t sigma plus psi times y sigma of t sigma. So this is the ODE system. Yeah. So till now we have seen influence dynamics as influence spread, but another interesting thing that we are going to look at now is basically influence dynamics, but on a single node. So it's important to understand how influence actually acts on a single node, or how a single node actually processes information in a social network to actually capture the influence dynamics across the network. So the first three works actually looked at influence dynamics on a network spread. Now we are going to look at a single social network user. So one of the features that you can observe across social networks is that most of the social networks actually display the content to you in the form of a timeline. So timeline is basically for people who are not on Facebook or Twitter, it's like your email inbox, not the priority inbox one, but the regular reverse chronological email inbox where content actually comes in. It's like a queue where content is pushed in from the top. So basically this is the way user actually processes information, and there are also different, variants of this are seen in different social networks. Some use parallel timelines, some actually sort the timelines. They are no longer reverse chronological. They actually sort it according to how they perceive that you will interact with the content. So but most of these social networks actually use a timeline based interface. So now we can actually see that people who are on Facebook can actually see that advertisements are the basic revenue mechanisms for most of the sites on the internet, and traditional online ads are something like banner ads or sponsored search slots, which are on some corner of your page, and the interaction with that is much lesser than interaction with some content which actually falls on your timeline, because timeline is where most of your engagement is. And one more thing is that these ads cannot be generally shared to your network. So the ads that fall here are actually customized to your interaction because they're on your social network rather than on your Google search page, and they're also shareable across your network. So you can see that more and more content providers and content creators are trying to advertise on the timeline rather than on the banner slots. So, and one more thing is to be noted is that user attention. This has been studied extensively by putting eye trackers on subjects. Basically, what they see is that most of the users interact like this with the content on the page. The above the fold interaction is basically the top 800 pixels, and it actually significantly decays. This is like how often do you go to the second page of Google results or something like that. So basically, it says that if you want to influence some user, your content has to be on the top of whatever list you're showing, because everything is on a list. You want to be on the top. So this is something that we want to study. So basically, you have a limited list, and people are actually pouring content into it, and their utility is in terms of how often they are found on the content timeline, or how high they are found. So we actually look at two different variants. I'll just quickly run through the models for the lack of time. So basically, this is a very simple setup where it's a finite timeline. So there is k entries. So there is only top k that is shown to you, and there are capital C users, capital C content creators who are pushing content into it. Their only control is the rate at which they are going to push the content into your timeline. And the timeline actually evolves as you would expect. When a new content comes in, the bottommost content is pushed out, and the new content comes on top, and everything else is pushed down like a stack. So basically, you want to look at, so the utility here is basically what is the stationary probability that my content is somewhere on the timeline. So if you can actually define it as, so I'll go to this directly. So PIC is the probability that content C is on user I's timeline, and you can actually show that it's, intuitive way to grasp this is basically this. So these are the rates at which contents are actually being pushed down. So each of these entries can be one of the contents of the C in a proportional, the rate proportional to the total rate. Basically, this content can be content 1 with the probability nu 1 over capital nu, which is capital nu is the sum of all the rates. So basically, each of these entries are like that, and alpha C is basically your competing rate to content C. So you take content C and look at all the rates of the nu minus C. That's the general notation for that. So you just look at probability that all the contents on the timeline are not mine. So that's this probability alpha C, and your content is somewhere on the timeline is 1 minus that. So if you take this as the utility, and you have a cost in terms of the rate that you're using, you can actually show that. I'll go to the direct result here. So we are considering a symmetric game where each user's cost for increasing rate is symmetric. So all the users have the same cost. So here it turns out that so you have a timeline of size k, and you have n players competing with you. All are similar. So now the question is, as number of players competing with you increases, what should you do? Should you increase your rate, or should you decrease your rate? It turns out that the answer is actually non-monotonic. You should actually increase the rate till the competition is equal to the number of slots that are available. So basically, if the timeline size is of size 100, and there's only 2 or 3 people who are competing, then without increasing your rate, you can find yourself somewhere on the timeline. So you don't have to invest a lot. But as the competition gets closer and closer to 100, then you have to increase your rate. If the competition is, say, 10,000 or a million, then there's no point in increasing the rate, because your probability of finding the timeline is a utility, but the cost is actually linear. So basically, increasing the rate beyond a point is actually, beyond a point here exactly is the size of the timeline itself. So you have a non-monotonic behavior here. And so this is the case of a finite size timeline. And you can actually extend this to the infinite timeline case, where you actually say that the timeline can be scrolled infinitely, but users actually stop at a point which is geometrically distributed. Basically, what you say is that if you've seen till 10th post, the probability that I'll see the 11th post is again with probability alpha, I'll go to the next post, or I'll stop right here. So the number of posts that you scan is geometrically distributed. And so now the question is, and one more thing is that different contents on the timeline can have different influence. Basically, the content quality can determine how influential the content is. So you can actually capture that in this model. I will not go into the details of this, but this is basically a study of competition on a timeline, but the timeline is, the model is much richer in the case that it captures the quality of the content, and also the size of the timeline is no longer limited. And so basically what happens is, so you can look at one particular content, its influence actually, so basic influence of a single content is basically a weighted combination of where all it is present in this timeline. So for instance, if my content is present on the first entry and say the fifth entry, then the first entry will give me an influence of B1, and then the fifth entry will give me some alpha power 4 times B1, because the probability that so you just sum that up, that is, and I can actually look at the trajectory of how this influence changes. So over time, as people start pushing content into the timeline, it can actually go down because someone else pushed the content, and it can go up because my content came in, and so on. So what we want to know is how can we capture average of any single content on the timeline. And so to do that, you want to show that there is a stationary distribution for this V of t process, and establish that there is an f, and once you know that there is an f, you can actually use level crossing analysis. Basically, level crossing analysis says that, I mean, it's a common tool used in queuing theory. You draw a level on this graph, and then you say that look at all the rates of transitions down, and look at the upcrossing rates, and these two rates should be equal because now the system is in stationarity. So you can actually write down the downcrossing and the upcrossing rates of that level, and using that you can actually so I'll go to the final expression here. So people from ECE can actually see that this actually resembles something that is this is without alpha. If alpha is equal to 1, it means that the user is actually seeing the entire timeline. So the entire workload is actually there in the timeline. So this 1 minus nu b, EB can be seen as the service, the expected service, and in the case of the MG1 queue, it's 1 over nu. So basically, this is something like the 1 minus rho term, which is in the MG1 system the probability that the queue is empty. And people might recognize PK from this. When you set alpha equal to 1, the expected influence of a user looks like this. But problem is that here alpha is not equal to 1. You actually have an expression that is so to compute EV you require EV squared and so on. So we actually use successive approximation to actually compute these EVs. And I mean, okay, I think I'll skip to the summary if you have any questions. So so basically done here is the last work is basically we have used a richer model of the timeline, and we have actually captured how the influence of a single user evolves over time, and then you can generalize it for multiple content case. And once you have a characterization of multiple content case, this is an interesting contrast with the earlier system, where in the earlier system, as number of users increased, there was a non-monotonic behavior of the user. Basically, you increase the rate till some time, and then you decrease. So you can actually show that as number of competitors increase, you should decrease your rate, because because basically, if you look at the utility across the rate, which is actually giving you diminishing returns, and the cost is going to be linear, and therefore you should actually decrease competing. Looked at some two-player competition on the. So I'll summarize now. Basically, we've looked at four different. I mean, I've presented four different problems here. First is the problem of influence maximization, where we've looked at analytically characterizing the influence spread for an LT model. We found out, we computed the optimal seeding set and interpreted the analytical expression using acyclic path probabilities in a Markov chain. And using that insight, we actually proposed a efficient sieving algorithm for influence maximization. And we then studied a fluid limit characterization of influence, and we showed that for a specific threshold distribution, it is equivalent to the SAR epidemic model. And we also showed that this can be extended to heterogeneous communities. Then we studied a model in which there was co-evolution. Basically, instead of single influences, you had multi-layered influence spread. One is the other is of the content itself. And we showed that a time threshold policy is optimal in the delay cost sense. And finally, studied content competition. And I didn't present this competition over multiple social networks. computation over timelines of finite timeline model and the infinite timeline model. So I would stop here, and if you have any questions, I'd be happy to answer. Yeah. Yeah. No, so in the Chem paper, there is actually an equivalence between a generalized version of the threshold model. It's no longer linear, but it's a generalized threshold model, and another cascade model, which is it's not independent. It's they call it the decreasing cascade model or something. So they construct generalized versions of LT and IC, and then show that these two can be shown to be equivalent. But I don't think there is any characterization of some fluid limit kind of analysis or some other way in which you can show that IC, the independent cascade model, goes to one of the epidemic models. Yeah. No, I haven't explored the fluid limit characterization of the IC model. So, yeah, okay, I get what you're saying. You are saying the evolution of IC model is very similar to how an influence happens in the SAR case. No, the point is that IC and LT are directly not equivalent. Only generalized versions of both are equivalent. So that's where, I mean, but IC models are very similar to the models that are generally studied in branching processes, but I'm not so familiar with that literature. No, it was completely in the ODE. So we looked at the monotonicity properties of the ODE. Yeah. Yeah. So once we went to the limiting system, we were interested only in the characteristics of parameters in the limiting system. So the finite end system, I mean, there are results, for instance, like the gas paper, where I mean, we didn't we didn't bring it back to the finite control. Yeah. No. That's what I said. That's a sieving threshold, and it depends on how. So there could be ways in which you can compute the alpha based on the graph structure. So it basically says how strict should I be in terms of filtering out the nodes. So I think that depends on the underlying graph structure, and I mean, but what we see is that it's easier to actually sweep through the alphas, and there is I mean, alpha equal to 0 or 1 is yeah, that's what I said. You actually sweep through the values of alpha to find the optimal alpha here. Yeah, it's data set dependent, and I mean, it depends. I mean, optimal is the wrong word. It basically says the closest alpha that you can use. So it depends on the resolution that you can sweep and all. No, the G1 sieving does not have. So basically, G1 sieving is an approach to show that you can minimize the number of computations in. So the complexity wise, it's significantly lesser than the greedy algorithm. But the greedy algorithm has, most of the algorithms which followed greedy have approximation guarantees in very specific graphs. So they say that in a general graph we cannot give any approximation guarantee. In some, for instance, there was an algorithm that I said CELF, which it has a 1/2 into 1 minus 1 over E approximation guarantee. But that's for a very specific set of graphs. Yeah. Yeah, that's what I showed. If you So if you look at it, this black curve is the one that had no sieving. So this was the using along with the dummy nodes. And as you increase the alpha, you are becoming more and more lenient. Yeah, so these are some of the publications from the research. I would like to take a couple of minutes to acknowledge a few people. First, without the guidance and motivation and patience of Anurag Kumar, I could not have finished this work, and he's actually a never-ending repository of knowledge and enthusiasm for this work. He gave me the necessary enthusiasm and motivation to pursue a non-traditional problem sitting in EC, and oftentimes he has been either the beacon and or the tugboat during my PhD. And I would like to thank the faculty of ECE, Math and CSA for the wonderful courses that took him. And special thanks to Professor Rajesh Sundaresan was here and Professor Narari for their interactions on the problems. And I also wish to thank, and in fact the problem was started in Professor Narari's lab when I took the game theory course, and I think a couple of, we had it as a semester project, and I think Lalita and Chandrasekhar here were actually part of my team there, and the sieving algorithm, the initial phases of that came up during that project. And I would thank my collaborators from India, France, Professor Ethan Altman, and I would like to thank the staff of Network Office and EC Office. And with these people, life at IISc would have been very boring and incomplete. So I would like to thank past and present lab mates of NEL and all my friends from ECE, and especially special thanks to Amos gang. I mean, it's really a gang, a big gang, and I would like to thank them mainly for keeping me sane during the PhD and with the necessary dose of insanity. And I would like to thank my friends from Rhythmica, the IISc music team over here, and this is for all the friends that I made through music and the music I made with these friends. And finally, I would like to thank my parents, and I mean, it's not thank, but acknowledge my parents and sisters for their unconditional love and support. And finally, Hofstadter's law is something you may not have heard. It says that it always takes longer to finish some task than you expect, even after you take into account Hofstadter's law. I think this is a homage to the essential spirit of the graduate student. And I would like to acknowledge all the graduate students who have not acknowledged themselves in their slides. Thank you.